Let's do that. All right. And I'm going to share my screen so I can write things for you. So just give me a second for this to work. Okay, screen thing. Done, done. Okay. Chat. Let's put that there. It's here. All right. So just stop me, please, as we're going along if you need more time or you have a question. It's better to ask. So okay, so we're going to talk about solving linear systems of equations. In this, at this point in the course, we're talking about algebraic equations. Okay, eventually we'll get to differential equations. All right, so before we get into this, just a little bit of terminology. So we say that a function f is linear if two things are true. Okay, so we're being a little sloppy here. About the domain and range of this function. Because it's linearity is a concept that makes sense in many different contexts. And it's a little bit technical to try to do this precisely. So I just want you to get the sense here. A function where some constant times the argument, you can multiply that, or you can take that multiplicative constant out in front. All right, so something like f takes x to 7x, right? That's a linear function. So f of x equals 7x would be another way of representing that function. So notice that if I, actually, so I want more space. So does everyone have what they need on this page before I go on? Are you good? Okay, I see some thumbs up, so good. So these are two notations for defining functions. You might see the first one in some contexts. The second one, probably, this is what you used to from calculus classes. Each of these is saying that the function takes the input x to the output 7x. So this is a linear function because it satisfies those two properties that we just talked about. So f of cx would be, well, what does the function do to its input? It takes 7 times the input. Okay. And that c we can factor out. And 7x is just f of x. Right, so we see that we have that property we wanted. Function of some multiple of the argument, we can move that multiplier out in front. And then we also have that second property. So let's see what happens if we take the function applied to the sum of two things in its domain. Oops. So that's 7 times x plus y. We can multiply out. And that's f of x plus f of y. Right, so the two properties we said we wanted are satisfied here by this function, so it's a linear function. Now, not every function, of course, is linear. So if we look at another function, so let's say g of x equals x squared. Well, what's g of c times x? It would be cx quantity squared, which is c squared times x squared. And in general, this is not equal to cx squared, which is cf of g of x. Okay, so c is not equal to c squared in general. So this is not a linear function. Okay, and you could check the other properties not satisfied either. So let's do that. Okay, so this is a function where neither of those defining properties for linearity is satisfied. You just need one of these to fail for the function not to be linear. And what's interesting is that linear systems of equations you can think of as well as being linear functions. So if we look over here, right, what was our function? It was just a constant times our input. Well, what if the input is a vector? So maybe we have something like this. Put a where A is a constant matrix. Well, f of some constant times x is our matrix A times cx. And we'll see later. We'll talk in a little bit more detail about matrix algebra later, but in fact, it's okay to move that multiplier c out in front of everything. So that property works. And similarly, we apply this function to the sum of two vectors. That just means take the matrix, multiply by the sum of the two vectors. It turns out there's a distributive property for matrix multiplication. So that works the way you would like it to. Okay, so linear algebra gets its name because of the fact that it is basically the algebra of functions of this sort. And functions of this sort show up in lots of equations that we would like to solve. So this subject is important because it's very useful. So we're going to develop some of the theory here, and we'll actually see how to solve equations where we have some function of this type is equal to a specific vector. Okay. Okay, so just to motivate a little bit why we're doing this, this is a ridiculously simple equation, right? X is unknown. We want to solve for X. A and B are coefficients that we can assume to be known. Well, how do you solve this? We can multiply each side by 1 over A, or divide each side by A. Notice that 1 over A times A is 1. And we can write our answer as a fraction. Well, the generalization of this is really what we're going to be talking about. So let's think about the possibilities here. So one possibility is that if A is not equal to 0, it's okay to actually do this, and we find a unique solution. The other possibility is that A is equal to 0. Okay, and if A is equal to 0, 0 times anything is 0. Then there's two sub-possibilities. If B is not equal to 0, there's no solution. And the other sub-possibility is that B is equal to 0. So in that case, our equation becomes 0 times x is equal to 0, or 0 equals 0. And it doesn't matter what x is. So there's infinitely many solutions. Okay, so we will see that when we go to the case of a system of linear equations, so if we have a problem that looks like this, AX equals matrix A, coefficient matrix A, times vector of unknown X equals our vector on the right-hand side B, we have exactly the same possibilities. If something about this matrix is true, the solution is unique. And then when our matrix coefficient doesn't satisfy that special property, either this linear system will have no solutions or infinitely many solutions. All right, so the fact that we have this structure is due to the fact that we're dealing with a linear equation, independent of the context, whether it's just one equation like this and one unknown, or if it's a linear system like this. Okay, so that's the power of mathematics, that you could recognize these patterns and use what you know in some situations to guide you when you're dealing with other situations. All right, so are there any questions at this point? Everybody good? Okay, so we're going to at first restrict ourselves to vectors and matrices and linear systems with real coefficients. Okay, we will see as we go along that, in fact, we're going to have to deal with complex numbers in some form, even if our systems have real coefficients. But let's not worry about that for the moment. And we're going to say that if we have a real m by n matrix, let's call it A. And remember, when we write the dimensions of the matrix like this, what is the first number they are talking about? Do you remember from last time?
It's a row.
That's the row, and then the n is the columns. Good. Very good. So we say this is in the space. Script m for matrices, m by n. So the set of matrices with m rows and columns, and that funny r represents the real numbers. This is the context we'll be using for now. Later, we might worry about the set of matrices where we allow the entries to be complex. Okay, so how many people have seen complex numbers before? Do you guys know what that means? Real numbers versus complex numbers? Tucker, do you want to
I mean,
explain?
we learned a little bit about it in the physics class I took over the winter,
Okay,
but we didn't go super in depth.
okay, so let me just so if you wanted to solve this equation algebraically, you would need a number whose square is -1. And if you think about it, when you square a positive number, you get a positive. If you square 0, you get 0. If you square a negative number, you get a positive number. So there can be no real number solutions to this equation, x squared plus 1 equals 0. Sometimes we really do want to solve this. We have to make sense of what a solution of this means. So we introduce a number I called the imaginary unit, which is the square root of -1, whatever that is. And if we build numbers in the form a plus bi, where a and b are real numbers, then all the numbers of this form are the complex numbers. And it turns out that these are, in some sense, easier to work with than the real numbers, because any polynomial equation, you can prove that the solutions are in general going to be found, all solutions are going to be found as complex numbers. Okay, so just working with complex numbers in some situations is easier because that will guarantee that you can find all the solutions of the problem. All right, but let's put that aside for now. For now, we're going to worry about real numbers. And we talked about the notation before. Oops. Okay, so if we want to refer to the entries of our matrix A here, capital A with the double underline is our matrix. Typically, we use the corresponding lowercase symbol for the entries with, remember, this is row subscript and then column subscript. Okay. So we can talk about vectors as well. And let's say we had a vector v here that looks like this. v1, v2, all down to vn. So this is a vector. I'm going to call this a vector sometimes, but notice that this is just a special type of matrix. Right, so the set of matrices, and in this case, we have n rows and one column. And if all of those entries are in the real numbers, we can say it's in the set of matrices of n by 1 matrices with real coefficients. And as far as MATLAB is concerned, it really doesn't make a distinction between vectors and matrices. You just have to keep track of the dimensions of your object, and MATLAB will treat it correctly. Okay. All right, so let's say we want to solve linear systems. Let's say we want to solve linear systems. Now, here's a fairly simple linear system. Okay. And notice that we can rewrite this. Using our matrix and vector notation. Okay, so what we have here is called the coefficient matrix. We sometimes call this the right-hand side or the forcing. And we say the system is homogeneous if the right-hand side is 0, right? In this case, I mean 0 vector. Otherwise, it's a non-homogeneous system. So homogeneous, non-homogeneous, depending on whether our system looks like AX equals the 0 vector or AX equals some right-hand side vector with B not equal to the 0 vector. So this is homogeneous, and this is non-homogeneous. Now, if you go back and think about that problem, AX is equal to B, where AX and B were all numbers, homogeneous would just mean that B was the number 0. Non-homogeneous would just mean that the number B was a number other than 0. Okay, so how would we solve this system with that terminology inserted there? Well, we know this is a non-homogeneous system. We have lots of strategies that we could employ to solve a 2x2 system like this. So when we say m by n system, we're talking about the numbers of rows and columns, right? So think of the subscripts of the coefficient matrix. And let's say that we solve that second equation for x1, or we could solve the first equation for x2 and plug in to the other equation. So let's say we look at that first equation. So from the first of these, we can isolate x2. We can plug this into the second. So negative x1 plus 3 times x2. That's going to be 11. Oops, and this was x1, sorry. All right, so that's 6x1 minus x1, that's 5x1 plus 6 is equal to 11. 5x1 is equal to 5, or x1 is equal to 1. And once I know that x1 is 1, I can use that to get my x2. Right, so x2 is going to be 4. So we've got a solution, and let's actually verify our solution here. So if x1 is 1, x2 is 4, this first equation is going to become 2 minus 4 is negative 2. That works. If we plug these values into the second equation here, minus x1 is negative 1. 3 times x2, that's 3 times 4 is 12. 12 minus 1 is 11, and that works. So We found a solution. We verified it works. If you think about the steps that we did in going through here, it should be clear that we found all the solutions. None of the operations that we did might have introduced extra solutions or somehow lost solutions. So we found in this case that our system has one and only one solution, or in other words, a unique solution. Now, if you think back to our AX equals B example, the possibilities for solutions, remember, were one and only one solution when our coefficient A was anything other than 0, and either no solutions or infinitely many solutions when A was 0. So something about this pair of equations is similar to the fact that this coefficient A in the single scalar equation was not 0, right? Or in other words, there's something about our coefficient matrix here that's telling us that we have one and only one solution. Now, maybe that sort of breakdown was special to this single scalar equation, right? How do we know that the same type of things can happen with two equations and two unknowns? Well, let's think about the geometry. Something like AX plus BY equals C, that represents a line. Right, so this is the XY plane. So if you think about it, when you have a system of two equations and two unknowns, two linear equations, two unknowns, what you really have is a line for each of those equations. And if you have another line for the second equation, there's going to be one point in the XY plane that corresponds to both of these equations. That's going to be the solution of the linear system, the single or the unique solution for the linear system. Okay. But that's not the only way two lines could be arranged in a plane. You could alternatively have two lines that basically live on top of each other, right? In which case every point works for both of those equations. So there's infinitely many solutions. Or you could have two lines that are parallel to each other. Okay, so there's no point in common between the two equations. There's no solution common to the two equations, so there's no solution for the system. So in fact, it is the case that what we noticed for our single scalar equation also happens for a pair of two linear equations. And we say that, some terminology I need to get down here. So does everyone have what they need off of this page? Everybody good? All right, so we'll go on. you say our system is consistent, if it has a solution, by which we mean it has at least one solution. Okay, so could be unique, or it could have infinitely many solutions. Okay, if it's a linear system, you can't have a situation where there's 2 solutions or 10 solutions. It's either one solution or infinitely many. Okay, so that's the point here. The features that we noticed for our single scalar equation and for our pair of 2 equations are exactly the same. Right? You have one solution, or you have infinitely many solutions, or you have no solutions. The system is inconsistent it's said to be inconsistent if it has no solutions. Okay, so those are the possibilities. And just like we did with lines in the plane, we could think of 3 equations and 3 unknowns, and look for intersections of planes in 3-dimensional space. That becomes too hard for me to draw, so we're going to take a more algebraic approach at this point. And we're going to start this in the 2x2 context. Okay, so let's think of 2 equations and 2 unknowns. A, B, C, D are coefficients, assume real for now. F1 and F2 are coefficients. We can assume they're real for now. We want to solve for X and Y. Right, X and Y are the unknowns we're trying to solve for. All right, so let's try to do this in a way where it's not too hard to see what's happening. So let's multiply that first equation through by C. I don't know. Let's multiply the first equation through by D, actually. ADX plus BDY. So multiply every term by D. So we're assuming D is not 0 when we do this. And let's multiply the second equation through by B. So if we do this, we're going to assume that B is not 0 as well. Okay, so multiply by b in every term in the second equation. And we did that to arrange for the y terms here to have the same coefficients. So if we subtract, let's group the x terms together. Okay, and then we can isolate the x. So we've actually got a formula for the x, and we could do the same thing to isolate y. To isolate the y, we could multiply the first equation through by c and the second through by a and subtract one from the other. So does everyone have what they need from this page? Everybody good? Okay. So ax plus by. Okay, so if we multiply the first equation through by c, and multiply the second equation through by a, notice now we can subtract to get rid of the x terms. And I'm going to take the second equation minus the first equation. Then I'm going to isolate y. All right, so let's think about those two solutions we found. In each case, we have to divide by the quantity AD minus BC. AD minus BC on the bottom for the x, AD minus BC on the bottom for the y. So as long as AD minus BC is not equal to 0, the solution is unique. If AD minus BC is equal to 0, then we may or may not have solutions. So there may be no solutions. Right, so notice that for the x, if AD minus BC is equal to 0, then I can solve for x if and only if d times f1 minus bf2 vanishes, in which case x is arbitrary. And if AD minus BC is equal to 0, I can solve for y if and only if AF2 minus CF1 is 0, in which case y is arbitrary. Okay, so we have exactly the same breakdown we've seen before, either unique solution. If there's not a unique solution, there may be no solutions or infinitely many solutions. If it's solvable, if the system is solvable, we either have one solution or infinitely many solutions. Now, we sort of have a little bit more freedom when we're dealing with a small problem like ax equals b or the set of two equations. It's not so hard to do the algebra directly. It's not so hard to visualize geometrically what's happening. This becomes a lot more difficult when you have more unknowns and more equations to deal with. So we would like to develop a more systematic way of attacking these problems. Okay. And we're going to also have to deal with some other complications. So the types of systems that you might want to solve will not always have the same number of unknowns and equations. Okay, so we want a more systematic way to deal with these problems that will let us deal with general systems where there might be a mismatch between the number of unknowns and the number of equations. All right, so before going ahead with that, just a note. If there are fewer equations than unknowns, oops. Then we say the system is underdetermined. And if an underdetermined system is consistent, there are infinitely many solutions. Okay, and you can see that sort of geometrically. Where is that? So if you think about the problem with two unknowns, right? The graph of a line, right, has infinitely many points on it. So By is, so this is one equation and two unknowns. So this is underdetermined. And as long as, let's say B is not equal to 0, notice that whatever X I want to put in there, I can work out a Y. I've got infinitely many points on the line that work as solutions. All right, so that's, again, this is a specific example. This is sort of the general structure. The general structure is always the same for linear problems. So this is essentially what's always going to happen with linear problems. You're always going to get infinitely many solutions if your system is underdetermined and consistent, if you can actually solve it. Okay, so So there is a method called Gaussian elimination. Okay, which will let you solve linear systems. And a version of this, in fact, is exactly what MATLAB has implemented, at least in many situations, to solve sets of linear equations. If you use MATLAB to solve linear equations, there's a high probability you're using some form of Gaussian elimination, sort of in the background. So it's important to understand the mechanics of doing Gaussian elimination. So we're going to go through it a little bit. The idea is simple. It's a little bit tedious if you have to do this by hand when the system is too big. So we're not going to go too crazy with doing this by hand, but it is important to understand the theory of what you're doing here. All right, so before we go on, are there any questions? Guys doing okay?
Could you go back to the previous page and notes just for a second, please?
This one?
Thank you.
Do you just need a little time to copy, or?
Yeah, I just didn't get like the very last line.
Okay, go ahead. All right, are we ready to go on?
Yeah, I'm good. Yeah.
All right. Right, so let's think about the structure. So it's a little silly to think about a 1-by-1 system in terms of matrices and vectors, but in principle you could do it. We actually went through dealing with a 2-by-2 system, and essentially when you solve the system, your solution takes the form of for each unknown, you have an equality. You know what the unknown is equal to. Okay, so our strategy in Gaussian elimination essentially is going to be to try to manipulate our algebraic system that we start with so that it's going to look something like this, where we've isolated the solutions of each of the unknowns. And the coefficient matrix here has a special form. Now, for now, we're talking about square matrices. And the identity matrix, or there are many identity matrices, but we can say identity matrix sub n is a matrix that looks like this. Now, let me just give a specific one. Okay, this is I sub 4 or the 4-dimensional identity matrix. It has ones where the row index equals the column index. So let's see here. Over here, we're in row 1, column 1, row 2, column 2, row 3, column 3, row 4, column 4. Those entries are all ones. Every other entry in the matrix is 0. So I sub 2 would look like this, right? So that's exactly what we need over here. I sub 3 look like this, and so on. And the n by n version of this is I sub n rows and columns. The entries where the row index equals the column index are all 1. Every other entry is 0. So our strategy in Gaussian elimination is based on trying to manipulate our coefficient matrix to look as much like these identity matrices as we can. The coefficient matrix may not be a square matrix, so we have to be a little bit flexible. So exactly what we're doing is the following. We're looking for the so-called row reduced echelon form. Okay, and we abbreviate this RREF for row reduced echelon form. Okay, if all non-zero rows are above any 0 row, B, first non-zero entry that means looking from left to right. In a row, and that's called our leading entry. So also known as the leading entry. Is a 1. And C, every other entry in a column with a leading 1 is a 0. Okay. So those columns with the leading entries are called the pivot columns. And those leading entries are called the pivot positions. Sometimes the leading entries are called the pivots. Okay. So this, is not coming out of left field. Essentially, this is exactly what we want. If we manipulate our linear system so that it's in Rref form, it's going to be the case that essentially that we can read off the solution to the system. So let's say, all right, so there's a lot of writing here. So let me know if you guys have this all down. We're good, okay.
I don't, and I have a quick question.
Sure, go ahead.
For that bullet point C, is that like how does that read?
Oh, what does it say? Every other.
Okay.
Sorry, I think I must have brushed against the text.
Cool. Thanks.
Smeared it. Every other entry in a column with a leading one is a 0. Okay. Everyone set? And does anyone need more time?
Yes, please.
Okay. Let me know, please, when you're ready.
I'm
Um,
good.
For letter A, what is the third word? Like after non, all non what?
Non-zero.
Okay, thank you.
Anyone else? Okay, so hopefully everyone's got this down. So here's an example. So let's say that we have a system of linear equations and we manipulate it so the coefficient matrix looks like the following. So 1, 0, 0, 0, 0, 1, 0, 0, -3, -3, 0, 0, 0, 0, 1, 0, 7, 2, -4, 0. Now let's think about our definition of Rref, right? All non-zero rows are above any 0 row. So this is the only 0 row. It's at the bottom, so we're good. Bullet point B was the first non-zero entry in a row, where the leading entry is a 1. So first entry is a 1, first entry is a 1, first entry is a 1. Okay, so we're good. And our last bullet point was that every other entry in a column with a leading one is a 0. So for this column, we've got our leading 1, every other entry is a 0. For this column, we've got a leading 1, every other entry is a 0. This column doesn't have any leading 1s. This column, we have a leading 1, every other entry in the column is 0. This column does not have a leading 1, so we're good. So this matrix is in Rref form. And if we think of this as being the coefficient matrix for our system, right, there should be 5 unknowns. right? Think about going across the row and down the column. Every row has, our coefficient matrix has 5 entries. So if I multiply this by a column vector on the right, there has to be 5 entries in that column vector, right? So this is a 4 row by 5 column. This is a 5 row by 1 column. What are the dimensions of the product here going to be? The 5s match, so we can multiply. The column is going to be 4 by 1. And we're going to have entries like that. So what happens if I go back to the actual equations that go along with our system? Well, the fourth equation has all coefficients of 0, right? So the left-hand side is going to be 0 equals whatever this entry is. So notice that we can immediately see, if we know the Rref form of our system, we can immediately see whether the system is consistent or not. And in fact, that's one of the things that makes the Rref form useful. You can actually use the Rref form in 2 ways, either just for the coefficient matrix or for the coefficient matrix and the right-hand side. You can append a column for that vector on the right-hand side and actually keep track of everything that's going on with your system of equations. So that's that enlarged matrix where you add the column for the right-hand side is called the augmented matrix. So both of those things are useful to think about. If we're, for now, if we're just thinking of this as the coefficient matrix in reduced row echelon form, notice what's happening with these equations. If we look at the third equation, so let's say the system is solvable. If we look at the third equation here, I'll have 0 times x1, 0 times x2, 0 times x3, and then x4 minus 4x5 equals whatever is on my right-hand side here. So notice that this is a system where there's fewer equations than unknowns. So if it's actually consistent, there's infinitely many solutions. And I'm actually set up here to basically read off the solutions from this Rref form of my matrix. So I can isolate x4, write it in terms of x5. Okay, and then if I look at the second equation here, that's going to be x2 minus 3x3 plus 0x4 plus 2x5 equals something on the right-hand side. And again, I can solve for x2. Now that's going to be in terms of x3 and x5. And in the same way, for the first equation, I can read off the value of x1 immediately. So with the Rref form, you can immediately read off whether your system is consistent or not consistent. If you have any mismatch between the number of equations and the number of unknowns, knowing that and the number of 0 rows, you can work out what order of infinitely many, exactly how many solutions infinitely many means if there are in fact infinitely many solutions. So here for the system, notice that x3 and x5 essentially can take any value you want if you have a solution. And the values for x1, x2, x4 are going to depend on those. Okay, so you have a 2-parameter infinite family of solutions. All right, so I don't think we have time in the remaining 2 minutes to actually get into the mechanics of manipulating systems to get to the RREF form. So I think that's where I'm going to stop for today. Let me stop sharing. So we have a few minutes. If anyone has questions, please ask. Otherwise, you are free to go and enjoy the rest of your day.
Hi, Professor. I just
Yes.
wonder how we can find the class recording.
I will get those posted for you, but they're not posted yet.
Oh, okay, got you. Thank you.
I have a quick question. For this class, are we only using the book that shows up on our WebAssign, or is there a second book?
So there is a book you have access to on WebAssign. There is a second book. I will post a link to that on the Canvas page for you.
All right, thank
The
you.
second
And-
book is free, so you don't have to pay for it.
Yeah. Is the second book referring to this class, or like what we're learning today and like yesterday, or is it the book on WebAssign?
Both of the books cover the material you need for 305. They're organized differently. And we're not following either one of them directly for the whole class. So you sort of have to pay attention in class and then go through everything we've talked about. You can find in either of the textbooks, but it's not
All
always
right,
going to be presented exactly in the same way.
All right, thank you.
Hey, Professor, I had a question regarding WebAssign. I tried to log into the class course, and it said that I was unable to register. It was something about, I forget the terminology, but essentially I was not able to get in with the
Yeah,
code.
I saw your message, Chris, this morning. I was hoping you would stay after class so we could talk about that. So did you try logging out, clearing your caches, and then going back in to sign up?
I did not do that. No, I tried a few times, but I did not clear the cache.
So try that. If that doesn't work, I suggest that you contact WebAssign support for help.
Okay.
Okay, because I can't. I don't work for WebAssign, so I can't go in and fix something for you. But try the WebAssign support. There's a link on the sort of the login page for WebAssign to student support. So go there. Let me just find that and I'll post it in the chat for you. Okay.
Sounds great. Thank
Give
you.
me a second. Let's see, WebAssign support, student support. Let's see here. Let's do this for everyone. Paste. Okay, so do you have that? Do you see that link I just posted in the chat, Chris?
I do.
All right, so go to that page. Shoot, where did it go? Here it is. So you can call, you can send an email. The quick start guide is linked there as well on that page. You should be able to enroll with a class key. So that's just the 4 steps in the upper left-hand corner. The simplest possibility somehow is not working for you, but try it again after you log all the way out of WebAssign, clear all your caches, and then go through this enroll with a class key protocol. And if that doesn't work, try calling the WebAssign support. Hopefully they'll be able to help you. If not, let me know, and I can try to escalate things for you.
All right, will do. Appreciate it, sir.
Okay, very good.
See you next class.
I'll see ya. Rishmika, did you have a question?